Okay, so it's great to see so many people here. Welcome. Thank you for your continued support of this series. And it's a great pleasure today to introduce our first speaker, Ville Suomala, who's from the University of Oulu, who's going to speak about sharp Farvard length decay of random Cantor sets. Over to you, Ville.
Thank you. Thanks for the invitation, and it's also great to be here and present this recent joint work with Pablo and Alan. So I'm going to talk about Farvard length of some random Cantor sets. So let me get started with something very classical. So we start with the Bezzecowitz projection theorem, which I'm sure everyone is familiar with. So we have a set with finite one-dimensional Hausdorff measure on the plane, let's say a Borel set, and if it's poorly unrectifiable in the sense that it intersects every rectifiable set in a set of measures 0, then the Bezzecowitz projection theorem, which is almost a decade old now, states that almost all of its projections have 0 Lebesgue measure. So one way to formulate this is to look at a more general concept. So if you look at the so-called Farvard length of a Borel set in the plane, which is for a general plane subset defined by looking at all of its orthogonal projections, looking and integrating the length of the projection with respect to the direction. So this is the Farvard length of a Borel set. So then another way to state the Bezzecowitz projection theorem is to say that a poorly unrectifiable set with finite one-dimensional measure has 0 Farvard length. And recently, and also, I mean, a bit earlier, there has been a lot of interest in somehow quantifying this Bezzecowitz projection theorem. And one way to quantify it is to look at the decay of the Farvard length if we look at the neighborhoods of the set. So if we assume, in addition, if we assume that our set E is compact, and if it's compact and poorly unrectifiable, we know that the Farvard length is 0, so almost all of the projections have 0 Lebesgue measure. And now if you look at the delta neighborhoods, we know that their orthogonal projections also tend to 0 as delta goes to 0. And then we use some monotone convergence theorem or dominated convergence theorem, and we can conclude that also the Farvard length of the delta neighborhood of the set tends to 0. And then it's a quite natural question and also a way to quantify the Bezzecowitz projection theorem for the set, for a specific set that we have on hand, to ask that what is the rate of decay for this Farvard length of the delta neighborhoods. Pertti Mattila, already in around 1990, he obtained a universal lower bound. Actually, Pertti's lower bound is in terms of the one capacity, but when we use Frostman's lemma, we can show that the Farvard length, we can see from this result that the Farvard length is bounded from below by the Hausdorff measure of the set. S here should be E. So Hausdorff measure of the set divided by log 1 over delta, where delta is the delta neighborhood. And these constants of comparability here, they are completely uniform here. And then it's quite, once we have, and this is actually, I mean, for general sets, this is sharp. I think for the circle, this is sharp with the correct formulation. And then it's quite natural to ask that can this really be achieved? So well, I mean, it can be achieved by rectifiable sets, but okay, so what did I say? Okay, so can this be achieved with poorly unrectifiable one set? Okay, so let's look at some examples that have been looked at in the research. So maybe the most studied and maybe perhaps the most relevant for what I'm presenting today is the most simple poorly unrectifiable one set you can imagine, which is the 1/4 Cantor set. So we start with the square. We place 4 squares on each of the corners of size like 1/4, and then we continue this in a self-similar fashion. And in the limit, we will have this well-known one-fourth Cantor set, which is positive and finite one-dimensional measure. And for this specific set, Nazarov, Perez, and Wahlberg, they have I think this is still the best possible upper decay that is available. So this is 1 over the log of 1 over delta, but now to some power. And I think the power that they have in their theorem is 1 over 6 or something slightly smaller than 1 over 6. So this is what we have in the deterministic situation. And remember that this completely universal lower bound that is valid for any Borel set would imply a lower bound with c equals 1. So there's still a bit of a gap here. And in fact, the same year, Bateman and Wahlberg showed that for this deterministic one-fourth Cantor set, this universal lower bound can be achieved because there is a better lower bound, which is log 1 over delta divided by log 1 over delta. Okay, so at least this deterministic example is not so it doesn't quite achieve this lower bound that holds for general sets. Okay, so then it's natural to start to look at some other. Okay, so I should mention here that this has been studied for not just for the one-fourth Cantor set, but many variants and also some product sets, and there's quite a bit of research that has been done on this in the deterministic setting. But now I will go to the random setting, and we have quite general results. So we have like an axiomatic situation of some kind of Galton-Watson type random one-dimensional fractals that we can treat in our result. But I will just present one example, which I think is the most natural example, and I think it's the one that is easiest to digest. So we start with the unit square, as in the definition of the four-corner Cantor set. But now we select 2 of the subsquares of half the side length, and we do this in a uniform way. So here are the 6 possible approximations of the fractal in the first level. So these are the 6 possible selections of exactly 2 dyadic subsquares of the unit square of side length 1/2. And then we iterate this in the stochastically self-similar fashion. So once we have selected the first 2 subsquares, we again, in both of the remaining subsquares, we select uniformly at random 2 subsquares, and then we continue this process for each n. Right. So this is what is also written here, but I think the picture explains what's going on. And of course, I have an example here where we have a realization with a couple of the first steps. So here's what the set starts to look like after 4 or 5 iterations now. So I hope that the model is clear to everyone. Yes, good. Okay, so this is standard to check that this has positive finite measure. It is Pauli unrectifiable almost fully, and it is even 1 alphas regular if you like. Good. Okay, so let's see what happens. So let's see if I can get that far. I'm already happy. So let's see what happens for the Farvard length of this random set. Good. Oh, okay, so we want to. So a priori, we would like to quantify the Farvard length of the delta neighborhoods of the set S. So if you're just interested about the rate of somehow the asymptotic rate, so the size up to a constant of the rate of convergence to 0 of the Farvard length of the delta neighborhoods, we could equally well just look at the Farvard length of these sets Sn, which are not precisely the delta neighborhoods. They are somehow quite good approximations of the 2 to the minus n neighborhoods. But if we just want to show that the decay is this log 1 over delta is the correct decay, we can just look at the Farvard length of this Sn. And the first step then we hope to have a Favart length to decay like 1 over log 2 to the 1 over log 2 to the n, which is 1 over n. Okay, so 1 over n is the expected plausible decay that we would like to have. Okay, that's what we would like to have. So the first step is to show that the expectation behaves this way. Because if the expectation of the Favart length doesn't behave this way, then there's absolutely no hope that we could have this Favart length of Sn to behave in this manner, that it would be comparable to 1 over n for all n. Okay, so this is our first theorem. I will perhaps, if time permits, I will discuss a little bit its proof, or at least some ideas in the proof. But once we have this expectation, this doesn't yet imply uniform. Of course, I mean, we know that the expectation is comparable to 1 over n. So what does it imply immediately? So it implies immediately that there is at least some subsequence that so that this Favart length of Sn will be comparable to 1 over n along this subsequence. So it implies instead of the uniform bound, it implies a lim-inf of the Favart length of the delta neighborhoods times log 1 over delta. This is going to be finite. But it doesn't yet imply the actual bound, which would be that this Favart length of S delta would be less than 1 over log 1 over delta, or let's say less than constant divided by log 1 over delta. So this is what we would like to have. And then we could say that, okay, this random set almost surely achieves this deterministic lower bound that was obtained in this Perthes result in the 90s. Okay. Anyway, so this is like the first step in order to solve this question. And this expectation theorem, as far as I know, in this for this example, I don't think it can be found anywhere. But for many related random models, it has been actually proved earlier. So Perez and Solomon already in 2002, they studied random variant of this four-corner Cantor set, and they obtained exactly this theorem and this corollary for that random set. And also Chang and Vardakis and Wahlberg have some one alphors regular unrectifiable random constructions where we have precisely this correct, so to say, correct estimate of for the expectation of the Favart length as delta goes to 0. So now our aim is to replace this lim-inf here by the lim-sup. And the key for obtaining this is the following limit law. So this could look, I mean, this probably looks a little bit surprising at first. So we show that so if you think about what does it mean? So our set is random. So also the Favart length is random, but the asymptotics of the Favart length is actually deterministic in this case. So the ratio between the actual Favart length of the end approximation of the Cantor set divided by the expectation of the Favart length tends to 1. And once we prove this kind of limit law, and then we combine this with the expectation, this will immediately imply the correct decay. So once we have these two results, then we are done if we are just interested about the kind of the magnitude of the Favart length. So this, as far as I know, this now gives the first examples where we can actually reach this deterministic lower bound for the decay of the Favart length uniformly in delta. Okay, but we still have some more. So we can actually also not just show that the Favart length is comparable to 1 over log 1 over delta, but we can also show that the limit of the Favart length of the delta neighborhood divided by log 1 over delta has a limit. So it converges. So we have very precise asymptotics here. So maybe it's not so important what this number is, but this number is something that one can actually compute directly. Or let's say one could compute directly. So maybe I have to explain this. So what is L theta t? So L theta t is a line, theta is the direction, and then t is a translation parameter. So basically theta is the direction, let's say with the positive x-axis, and then the t is how much the line has been translated in the direction which is orthogonal to the theta. And now we look at so the line is fixed, but our configuration at the first level, this is a random variable. So we have these 6 different options for this random variable. So it's a very simple random variable. It has 6 possible values. It has a variance. Okay, so it has a variance. This variance depends on this line. But then for each fixed theta, we integrate over all the translations of the line with respect to t. And this is some number that now depends on the direction only. And then 2 over this v theta we integrate over the directions, and this gives us a formula for the limit of the Farvard length of Sn times n, if you want to put it that way. That's actually the kind of the core of the theorem, is to going from Sn to the actual delta neighborhood is a small lemma, but okay, maybe I'll put the next slide already. So this is the actual theorem here, theorem C, that the Farvard length of Sn without this expectation even times n tends to some limit, which turns out to be deterministic in our case, which is a little bit surprising maybe here. Good. Okay, so I think these are almost all of my theorems now. So these are okay. So combination. So these are the actual things that one has to prove. Let me put it this way. So I have 3 actual things that I have to prove, and then combining the 3 results, we have the theorems that I had in the previous slides. So in particular, we have that the Farvard length will be comparable of Sn will be comparable to 1 over n. Farvard length of S, delta neighborhood of S will be comparable to 1 over log 1 over delta. And then we have this very precise asymptotic as in the previous slide, or as we have here in this theorem C. So far, I hope things are more or less clear. Then I have 10 more minutes, and I have to decide how to spend the 10 more minutes. Okay, so I think I had a purpose for this slide, and the purpose was that to say, or maybe recall, I said this already earlier, that this is only one instance of more general result. So, but I think as even for this specific example, I think it's already very it's new and interesting. But the method also, I mean, it works for this kind of let's say dyadic or L-adic subdivision models that produce one regular fractal sets. But there is some important condition that we need, which is basically that for each of the squares in the first level, the probability of selecting them is the same. So there's a martingale behind, if you want to put it that way. Okay. Well, maybe one more. Well, maybe I should. Yeah, maybe I should go through one more example. So I have one example, and now I have another example. So this is kind of so the first example is kind of generic. It's a non-degenerate case, and then there are some degenerate models where the behavior is a little bit different. Okay, so let me also explain this with a picture. So by a degenerate model, I mean a model where, again, in the dyadic setting, in the first step, we select 2 of the dyadic squares of side length 1/2. But now the selection is not uniform anymore. But let's say in this example, we select either both of the squares in the left column or both of the squares in the right column. And then we continue with this random choice in each of the remaining squares. So here you can see a realization, and again the couple of first steps. So the point here that how this is different from the kind of the non-degenerate situation is that now, as you can see, one of the principal projections here is always an interval. So in this case, the vertical projection is the interval, is the whole unit interval. And there's an analogous example where the horizontal projection would always be the unit interval. And this is, so here I mean, these kind of examples are precisely the ones where something slightly different happens. And here, so the decay here is not 1 over log 1 over delta, but it's log 1 over delta divided by log 1 over delta. And maybe if you know, or if you remember from the second or third slide, so this is precisely the lower bound, the best possible lower bound in the in the deterministic case. So the behavior of this the generate examples is the behavior, asymptotic behavior of the Farvard length in these degenerate examples corresponds to the lower bound in the deterministic case. Is this well, it's not a coincidence, but is this some indication for the deterministic situation? That I don't know. Okay, something like 9-10 minutes, I suppose. I have many theorems. I should decide what of them to prove. Okay, so maybe, well, this is kind of the expectation theorem. Maybe this is somehow the most essential, and the strategy of the proof in our example and also in this more general situation is inspired by the proof of Perez and Solomia for their randomized version of the four-corner Cantor set. Somehow, a priori, what we would like to show is that if we can show that if we could show that for each line, the probability of this line surviving n generations of the random process is at most a constant times 1 over n. If the constant is uniform, independent of n and independent of the line, we would be done. At least for this upper bound that the Farvard length is at most constant times 1 over n. And actually, in this example, this holds. So we could show that this holds uniformly, but in some other examples, it doesn't hold. And also for this example, when we want to compute the exact asymptotics, it's very beneficial to take a slightly different route. So it's slightly easier to show, and in some cases, actually, this is necessary that we allow some exceptional set. So we allow some exceptional set of lines which might depend on theta and n, but which is so small that it doesn't have essential effect on the Farvard length. So we try to show that this is true, maybe not for all lines, but for most lines where the exceptional set might depend on the direction and also on n. Good. Okay. Anyway, the starting point here is quite simple. So we look at the expected length of the line of the line that is of the line intersected with the set at level n. And this is because every point survives the first n steps with probability 2 to the minus n. We know that this expectation of the length of the set Sn along this line L will be 2 to the minus n times the original length of the intersection of the line and the unit square. But then we can also write this expectation, so we can condition on survival. So we condition on survival, we look at the probability that this line survives, and then we compute and then we multiply this with the conditional expectation, that what is the expected length of the intersection conditional on that intersection being non-empty. Right. So this already now gives us a hint that if we can bound this conditional expectation from below, if we can show that this is larger than n times 2 to the minus n, if we could show that this is true with uniform constant independent of n and the line, we would be done. And in this slightly easier way, maybe we allow some exceptional lines. Okay. I guess it's best if I just show some pictures. So how do we approach this? What is the general approach? So we write this expectation, so not even the expectation, but the argument of the function that whose expectation we are looking at. So this will be the line intersected with the set at level n and its length. So we split this in this kind of dyadic, how should I call them? Dyadic annuli, right? So here you can imagine what happens. So this is the large square is the unit square. We look at the intersection with the line on the intersection of the line with. So we fix some square at level n, and then we look at its dyadic ancestors. And then we look at the part of the line that lies in the dyadic ancestor at level I-1, but doesn't lie in the dyadic ancestor at level I anymore. So we have this kind of dyadic annuli, and we want to, for each of these parts, we want to compute the expectation of the length of the line intersected with the random set at level n. Good. And this we can actually do very precisely. I don't think I have time to go through this part, but this is actually it's very similar to some. It's akin to some let's say Carlton-Watson tree survival probabilities. So what should I say in the last 4 minutes? Okay, so this one can do, so I'm cheating here actually a bit. I'm cheating a lot, but how should I finish? Okay, so this red estimate here is our goal. And then if we could instead, if we could switch the conditioning so that instead of conditioning on something surviving along the line, if we could condition on a specific square surviving along the line, then it would be easy to get this estimate. So this is more or less a standard computation. It would be easy to get this estimate. But now the actual question here is that once we have this kind of conditioning, if we know that some square is surviving and a specific square is surviving, we condition on this, and then we estimate the expectation of the line intersection. Is this actually going to be useful? Because the thing what we really want to condition on is the that something along the line is surviving. So obviously this events that a fixed square is surviving along the line, it's not they are not disjoint. So we cannot just condition on this and then apply the formula of total probability. But what we can do here, and what already Perez and Solomiak did, and what is also kind of a standard approach in the corresponding problems for Carlton-Watson trees, is that we somehow specify the first element that survives. So here we would specify the first element from the, let's say in this example it works so that we could just specify the first element from the left that survives. So in this picture it would be this blue square Q. This survives, and then conditional on this, if we could still repeat the previous argument, then this would give us the desired estimate. And the point here is that if the picture is nice, then we can repeat the previous argument. So if the picture is like this, so if this first surviving square here is on the left to this dyadic annulus that I am looking at, then the conditioning basically works as before. So the information, so now here is a square at level I, and here is a square at level I-1. If it happens so that the first surviving square falls into this Qi along the line, and if the Qi-1 minus Qi is on the right-hand side, the conditioning works as before, and we get this we get this essentially we get this bound that we need. But it could happen that, okay, I will finish in 1 minute. So it could happen that and it does happen that while we zoom into this square, sometimes the picture looks like this. So this dyadic annulus is now completely on the left-hand side of this first surviving cube. And then actually we know once we condition on this cubing the first element that survives, that nothing here survives. So this is a huge problem. And another problem is that the length of the intersection could be very small. Okay, so the key here is that if this, so now think about this dyadic square, think about their symbolic representation with 4 symbols. That symbolic representation for most cubes is normal. It means that all the 4 possible symbols left, top right, bottom left, bottom right, appear roughly equal many times. So it means that for most squares, we will see this good picture at least a fixed proportion of times. And then we can carry on the estimate, and this will already give us the right decay for this Farvard length. Okay, so I don't think I have time to explain the limit law. I mean, this is actually it's not very complicated in this example situation. So we use some convexity argument plus some concentration inequality. But maybe I say one word about the exact asymptotics. So for the exact asymptotics, the first step, of course, here is that we know already that by this limit law that we can replace the actual Farvard by its expectation, and then we can try to refine the previous argument that I was trying to sketch for the correct decay, order of decay. And instead of using the normality just for the normality of the representations, we use a refined version where most of the squares are actually so that if we fix some large k and then we look at the sequences of length k in the symbolic coding of the squares, also these k sequences of the symbolic codings, they are normal. So that is the very briefly the idea here. Yes. So thank you.